I'm Sophie. As Will said, I'm a second year PhD student at Cambridge. I'm supervised by Alex Copley and Owen Weller. And I'm going to talk to you today about some of the UK's oldest rocks and what they can tell us about how the Earth worked in the Archean, which is about 3 billion years ago. So to start off with, I'm just going to give a quick overview of what we know about plate tectonics today and why we think there might be some interesting questions raised about whether plate tectonics worked the same way in the past as it does today. So, quick overview. Today we have a good understanding of the Earth's lithosphere. That's the crust and the upper mantle. And that's the part of the Earth which has got a conductive temperature gradient going from about 13 to 1400 degrees at the base to about 0 at the surface. And we know that the lithosphere makes up the Earth's tectonics plates, and that these tectonic plates generally act as rigid bodies. And these rigid bodies are moving due to forces acting on them, such as push from mid-ocean ridges and pull from subducting slabs. And we know that deformation is concentrated at the margins of plates in kind of long linear boundaries. We know this from a really wide range of observations on a range of scales. For example, we can use GPS observations and studies of earthquakes to determine how plates are moving and to observe where deformation is being concentrated. We can also use a wide range of larger scale observations to reconstruct past plate motions to some degree. And these observations include many things you'll have been familiar with, regardless of your level of geological background, including, looking at observations of fossil distributions across the globe, observations of where rocks of certain types outcrop across the globe, observations of magnetic stripes on the seafloor, and you may have come across how all of these things can be used to reconstruct past plate motions. Overall, we can build this picture of tectonic plates today. So you've got like a brief figure showing how we think tectonic plates are roughly split up today. And we can describe the different interactions we get where these plates meet, ranging from divergent margins where we get things like mid-ocean ridges, to convergent margins where we get mountain building or subduction, and obviously strike-slip margins as well. However, reconstructing plate motions, so thinking about how plates were configured if we rewind time and move into the distant past, becomes increasingly harder the further back in time we go. So the oldest oceanic crust is only 300 million years old, thereabouts. So when we're looking beyond 300 million years old, we're just relying on the outcrops we see on the continents to reconstruct the positions of these continents in the past. And we've got a kind of very rough figure on the right here showing how rocks of different ages are distributed across the globe. If we focus particularly on the very oldest rocks, so the rocks in this dark blue colour or this sort of mauvey purple colour, we can see that on the continents we do see these rocks, but they're pretty restricted and don't make up a big proportion of the global rock record. It can be really difficult from this to reconstruct past plate motions on Earth. And it raises the question, how can we be sure the Earth actually worked the same in the past as it does today? Our previous broad definition of plate tectonics requires the whole Earth to be comprised of rigid plates with deformation concentrated at long linear margins. These margins will sometimes show characteristic rock types. For example, and we'll talk about this more in a sec, high pressure, low temperature rocks at subduction zones. It's clearly going to be difficult to say with any certainty that one regime of plate tectonics was operating across the whole globe in the past, given this really limited amount of outcrop we have. However, we can at least look at the rock record we do have through time to see if it's consistent with the tectonic processes we see today. One particularly important geodynamic environment to think about is subduction zones, which people will often use as a marker for the existence of plate tectonics because it results in pretty distinctive rock types. So just as a quick reminder of the rocks we see in subduction zones. In subduction zones, our downgoing plate comprised of oceanic crust undergoes high pressure, low temperature metamorphism because the downgoing oceanic crust is fairly cold and remains colder than the ambient geotherm throughout subduction. So we see the oceanic crust, which is initially comprised of basalt, going through and generating a predictable series of rock types. So we're moving from basalt to green schist to blue schist into eclogite. And we get exhumation of these rock types as subduction progresses. So at the surface, we see outcrops of these high pressure, low temperature rocks. However, it can be really hard to preserve these rocks. So this is just a quick pressure temperature diagram showing rough stabilities of different types of rocks. So for example, if we're moving blue schists and eclogites back up to the surface, we can see that those rocks aren't expected to be stable at the surface. So if our rock experiences any subsequent metamorphism or introduction of fluid, there's a real risk of our rock retrogressing to something that potentially doesn't resemble a blue schist or an eclogite. So, bearing this caveat in mind, that it might be difficult to recognise rocks like blue schists or eclogites moving further back in time, where you've increased the risk of retrogression, we can start to have a look at the global rock record to try and place some bounds on when we have seen subduction by seeing where we see these blue schists and eclogites, which are characteristic of our subduction zone. So we have diagrams like these, which show compilations of the global rock record, and we want to focus here on the blue rocks at the bottom. So these are our high pressure, low temperature rocks. We can see that we're not seeing blue schists and eclogists preserved beyond about 2 billion years ago. And there are some questions as to whether those rocks are genuinely not there in the rock record or they're just not preserved. But observations like these have led people to say that subduction might not have occurred in the past, and thus global plate tectonics as we know it today might not have been present in the past. There's actually a massive amount of uncertainty regarding when plate tectonics started. So this figure here from a recent paper by Palin et al. Shows a range of dates that have been placed on the onset of plate tectonics by a number of recent papers. And as you can see, they're ranging from 4 billion years ago to sort of around 1 billion years ago. One of the big ongoing areas of research in this area is thinking about what processes might have occurred in the Archean if not plate tectonics. To do this, we've got to look at the areas of the world that expose Archean rocks and think about what geodynamic environments may have been responsible for the formation of the outcrops that we see in these areas. While we don't see unambiguous evidence of subduction in the Archean, i.e. those blue schist and eclogites, those low temperature, high pressure rocks, we do still see rocks which have probably moved from a near surface environment to the mid-crust. So in this project, we're thinking about how we can look at Archean rocks globally and unpick the environments where we're seeing rocks which seem to have moved from the surface into the mid-crust. Just to give a quick overview, Archean outcrops around the world are comprised of the Archean crust. We basically don't preserve any unambiguous ocean crust from the Archean. There's a broad split in Archean outcrops between those that are thought to represent the Archean upper crust. You might have heard of these referred to as granite greenstone belts, for example, and those representing the lower crust, which are often more homogeneous than upper crustal blocks, and are mainly comprised of quartz feldspar-rich rocks, which are called TTGs, which stands for tonalitic drongymitic granodiorites. We see rocks in most Archean areas at all trustal levels, that have been interpreted as moving from the surface to depth. These are called supercrustal rocks. For example, in the lower crust TTG terrains, you see rocks that don't look like the rest of the TTGs in terms of their mineralogy. The presence of these rocks suggests that some process has just juxtaposed surface rocks with mid to lower crustal rocks. The figure I've shown here shows a range of ideas that people have come up with that could generate these rocks. They range from uniformitarian scenarios, so scenarios that resemble processes we see today, like subduction, to non-uniformitarian scenarios like sagduction. I'm specifically interested in sagduction as a possibility, where rocks at the surface sag into the lower crust due to a density instability. This mechanism has been fairly widely discussed as a way to explain possibly supercrustal rocks in mid to lower crustal environments in the Archean. It's important to understand whether sagduction is viable, given that people have used this process to explain observed rocks in the Archean. While there's been a reasonable amount of work done looking at sagduction viability in the upper crust, not much work has been carried out in areas where sagduction has been invoked to explain juxtaposed surface rocks with crustal rocks in the lower crust. And as I say, it's important to understand what tectonic processes could have operated in all Archean areas that we see across the globe, to gain a picture of the best picture we can gain of the global geodynamic framework in the Archean. So in this study, I specifically looked at a test area in northwest Scotland to explore how geodynamic environment for possible supercrustals can be constrained. And I was particularly focusing on sagduction and whether that's a viable way to generate observed bodies observed in northwest Scotland. So in the rest of this talk, I'm just going to go through the methods used in this study. So I basically use information from fieldwork, petrography, and some phase equilibrium modeling. And I put that into a numerical model of density-driven sagduction to talk about whether sagduction scenarios are feasible over a pretty wide parameter space. So to think about the field area where I'm specifically focusing on, this is a zoomed in map of northwest Scotland showing where Archean rocks, so that's rocks of about an age of about 3 billion years, outcrop in the UK. These rocks are shown in various shades of blue on the left. The rocks that reach the highest pressure temperature conditions are in this darker blue, and they reach the granulite facies. These rocks probably represent the lowest crustal level of Archean crust that we see in the UK, and we have the zoom in of those on the right-hand box. The central region is relatively uniform, composed of those quartz feldspar-rich TTGs I was talking about earlier. However, the TTGs contain occasional outcrops of other lithologies. These are highlighted on the map in orange and grey and yellow, and these lithologies are what people have interpreted as possible supercrustal assemblages. The lithologies are garnet biotite felsic gneiss, mafic gneiss, and ultramafic gneiss, and I'll give you a quick overview of these in a minute. To carry out this study, I needed a range of samples, both from the possible supercrustal lithologies and also from the background TTG, because I needed to work out the difference in density and mineralogy between these possible supercrustal bodies and the TTG. So that is the things that may have sagged and the fluid into which they may have sagged, i.e. the TTGs. I'm initially going to focus on the Knocan Scythian site, as it's the largest possible supercrustal in the Lewisian and contains two of the lithologies I was interested in. So before I move on, I'll just quickly show you the lithologies we're thinking about. So just in general to remember, darker rocks are generally going to be more dense as they contain a higher proportion of mafic dense minerals. The TTG is our background, our possible fluid in this sagduction scenario, and it makes up most of the Archean terrains in the lower crust, and it contains mainly quartz and feldspar. We then have a garnet biotite felsic gneiss, which is getting slightly darker coloured, our mafic gneiss, which has got increasing amounts of pyroxene and garnet, and then our ultramafic gneiss, which will often contain purely olivine and pyroxene and maybe some garnet. Oh, sorry. There we go. To work out the pressure temperature conditions at Knock and Scythian, which I need to do so I can work out the density difference between the lithologies of interest and the differences in mineralogy between lithologies of interest, sort of during this subduction event, I used phase equilibrium modeling. So this is relying on the idea that different minerals are stable at different pressure temperature conditions. So like with our subduction zone, as pressure and temperature increase, different mineral assemblages form. The mafic gneiss at Knock and Scythian best preserves a mineral assemblage at peak conditions. And these images just show a thin section and ChemScan, which is a scanning electron microscope image of the mafic gneiss. And I found that the peak assemblage in the mafic gneiss was 2 pyroxenes, garnet, plagioclase, ilmenite, and liquid melt. And from this, I was able to construct a pressure temperature diagram, which is mapping out how the stable mineral assemblages change with changing pressure and temperature for our mafic gneiss. We see that the mineral assemblage I observed in the mafic gneiss corresponds to pressure temperature conditions of about 900 to 1000 degrees and 8 to 10 kilobars. These estimates of pressure temperature conditions for Knock and Scythian agree with pressure temperature estimates made for the rest of the region of the Lewisian that I'm interested in. So this diagram on the right shows a compilation of calculated PT conditions for the Lewisian. Taking that pressure temperature condition now as representative of peak conditions experienced by the rest of Knock and Scythian and the surrounding Lewisian, I then carried out similar pressure temperature modeling on all the samples I had got, so from Knock and Scythian and the other lithologies of interest, so my mafic gneiss, my ultramafic gneiss, and the TTGs. I was able to get density and mineralogy of these samples at those peak pressure temperature conditions, and that information is summarized here. So on the left, we can see densities calculated in this peak pressure temperature window for all of the lithologies. Averages for each lithology are shown by the colored lines. So we have TTGs, garnet felsic gneisses, mafic gneisses, and ultramafic gneisses. And we've also got a quick summary of the main minerals that are present in these lithologies. And the key takeaway here is that the TTG is dominated by feldspar and quartz. We can also calculate how the density difference between our possibly supercrustal lithologies and our background TTG varies over PT space. So just to take you through one of these diagrams, this one shows the density difference between our garnet biotite felsic gneiss and our TTG. This box here shows the peak pressure temperature window. The table down here shows the average density contrast between our lithologies in the peak window. And we can see from these plots that if we move down pressure or down temperature from our peak conditions, the density contrast doesn't change much from the value in the peak pressure temperature conditions window. So moving on to the modeling I was able to do, from our petrography and our fieldwork and our phase equilibrium modeling, we've now got possible density contrasts between our background TTG and our possible supercrustals. We've got a maximum depth that was reached by our possible supercrustals, and we've got a temperature constraint at that depth. So to model subduction, we used a Rayleigh-Taylor instability model where you have a more dense layer on top of a less dense layer. An instability develops at the interface between the more dense layer and the less dense layer, and a particle, you kind of get a drip coming down from the more dense layer, which eventually necks to form a particle. We can then use Stokes settling law to model this particle as a solid particle falling in a viscous fluid, where our solid particle is comprised of one of the lithologies of interest, and our background fluid is TTG. Using a Stokes-Settling model, we can calculate stress on the falling particle and strain rate in the fluid, and thus the viscosity of the fluid. We can then use mineral flow laws to explore what temperature would be required to give the observed fluid viscosity. And we can do this across a range of conditions such as body radius and the duration of a subduction event. From that modelling we did earlier, we have a peak mineralogy, and we know that the TTGs are predominantly feldspar and quartz, so their behaviour is going to be controlled by the feldspar or quartz flow law. So moving through one iteration of the model to kind of show you how this works, we have to choose a density difference, so choose a particle lithology, in this case the mafic gneiss, choose a radius of that particle, in this case 100 meters, choose a velocity which is going to be controlled by how long it takes to get to the surface from the depth. And from Stokes settling, we get the fluid viscosity that would be required to get the particle to its observed position. That's the black line on the graph. We can then use mineral flow laws to see how viscosity varies with temperature for the calculated strain rate, and also how this varies depending on the mineralogy and wetness. The different lines shown here are for quartz and feldspar, with wet and dry scenarios shown for feldspar. We can extend this model for different body sizes. So this is just the same plot we saw earlier, but we've now got body sizes which increase this way and increasing event duration. And we can explore how feasibility changes with changing these parameters. So we can do this firstly just by considering the mafic M member, which is what we've shown here. And we're just showing a dry feldspar flow law here. So the intersection between our black line and our viscosity is giving us the temperature that would be required for a body of that size with a feldspar flow law for viable subduction. And we can see how the plots on the left are translating to this compilation plot on the right. So we can do this, as we've seen, for a range of timescales, and we can see that timescales, oh, sorry, you can see we're nearly done. We can see that timescale is not that important, and that's because we're seeing a bit of a trade-off between event duration and strain rate. So kind of moving on to what we can get from this, we can plot curves like this for each possible lithology end member. So just to remind you what these lithologies are, we've got the pictures again, moving from garnet felsic gneiss to our ultramafic gneiss. So we're considering the density difference between the TTG and the possible supercrustal. And the red boxes are just showing some rough constraints from our observation of the Lewisian as to what would be reasonable conditions. The biggest supercrustal bodies in the Lewisian have radii of less than 5 kilometers. The temperature on the y-axis is representing the average temperature throughout the subduction event and is unlikely to be above 700 degrees. These constraints are being shown by the red boxes. And we can see that for a dry scenario, that's purple, subduction doesn't seem to be particularly viable. For a fully water saturated scenario, that's the pink and blue lines, subduction seems to be increasingly viable, though more so for a quartz flow law than a feldspar flow law. So we're seeing that subduction does not look particularly viable in the Lewisian case unless the lower crust is basically water saturated, which is not consistent with other observations of the Lewisian at peak conditions. So overall, it seems like subduction is probably unlikely to be responsible for the current juxtaposition of possible supercrustals with TTGs at the same structural level in the Lewisian. But water content is, in this case, a key factor in controlling subduction viability. So more work might need to be done to better constrain this. Sorry I overran a bit there. Thank you very much for listening. if you have any questions, please type them.
Yeah, brilliant. Thanks, Sophie. So yeah, Sophie says we'll have a few minutes for questions, I think. And if you've got questions, pop them in the chat. I know Sophie has got many questions and can probably start us off whilst people are typing away. But yeah, go for it.
Yeah, so I'm not sure if you covered this, but I was wondering how exactly are these sagduction events initiated?
Yeah, so kind of the thought is that if you've got a more dense layer on top of a less dense layer, you basically get the development of this thing called a Rayleigh-Taylor instability, which you basically see in like any scenario where you have a density instability, where any sort of small perturbation from completely flat at that boundary will develop, will increase in size, and you eventually get drips forming as these kind of wiggles get bigger in size, and as that drip sort of continues to fall, you get a blob. You'll get some form of blob forming, which in some cases will detach from the upper layer. And kind of the overall goal is to like completely overturn your density structure. But yeah, it's really cool. Like you see it, you can just kind of do it with like stuff in the kitchen if you I may have done.
So we have our first question in the chat from Eleanor. So she has two questions. The first one is, was your fieldwork/research affected by COVID-19 and how did you deal with it?
So basically I did the fieldwork for this project. I worked on a related project for my master's, which was more looking at the geochronology of the Knock-Scythian suite. So I basically collected the samples that I ended up using for this project in, 2018, I think. And so I meant to say this as I was going through. So the samples from Knock-Scythian are mine, and the samples from the mafic lithologies and the TTGs are from existing data sets. I would like to go and look at those rocks myself at some point. But yeah, I sort of ended up moving my project in my first year of my PhD to being more computational and based on data that I could get from other sources. Because yeah, obviously fieldwork was sadly not possible this year.
And the second part of that question was, how many samples did you have to collect for a clear understanding of the petrography? Yeah,
so this kind of, the area that I focused most on for my petrographic study, which didn't really come up in this, because I get for people with thin sections, this did not contain enough thin section images. But basically, the suite I was trying to understand, the Knock-Scythian suite, was mainly comprised of garnet biotite felsic gneisses and mafic gneisses. And like I spent a reasonable amount of time walking around in that area to kind of see what degree of heterogeneity I could observe in the garnet biotite gneisses. I think I ended up with 5 samples, which were sort of going across the range of compositions that I'd seen in the garnet biotite gneisses. I ended up using slightly bigger data sets than that for the other lithologies, just because the existing data sets contained, like, I think I ended up with maybe 15 mafic gneisses and 20 TTGs, and probably similar for the ultramafic gneisses. But yeah, I mean, just sort of to go to my density plot, like most of the lithologies, hopefully you can see that, most of the lithologies do sort of, they show quite a large spread, but like, I think from my sampling and from descriptions in the other papers, they do cover the observed heterogeneity. So I think this seems like a reasonable amount of samples to use, and you could probably achieve a similar result using slightly less or slightly more samples, depending on your area.
So I think in the essence of time, it'd probably be best if, because there's definitely a few more questions in the chat, and if we move on to Izzy's talk. And Sophie, if you want to answer any of the questions in the chat, feel free to. And I know Sophie and I and anyone else who wants to can stick around at the end, and if people have questions, then I'm sure we'll have some time. But yeah, so we'll move on to our second talk for now. So the second speaker is Izzy Carter, who did her undergrad at Oxford and has now moved to do her PhD in Krakow at AGH, and will be speaking to us about some field work done in Scandinavia, which I'm very jealous about, and I think everyone probably would be at this point as well. So yeah, Izzy, take it away.
Okay. Yeah, I will share my screen. That I'm not sure if that's shared the right screen. Okay, can you see my presentation?
Yeah, perfect.
Great. And I'm sorry if my internet goes dodgy throughout this. My likes to cut out in the middle of presentations. So if it is, I'll turn my video off. But anyway, hi, I'm Izzy. As Will said, I did my master's at Oxford, but I'm now at AGH University in Krakow in my first year of my PhD. But I'm today going to be speaking about my master's project, which was on exhumation of the Western Gneiss Region in Norway, looking at symplectite thermobarometry in eclogites which formed under ultra high pressure metamorphic conditions. So the Western Gneiss region is located in Western Norway. It's part of the Caledonian orogenic belt, which is a mountain belt that stretches through from North America, through East Greenland, Scotland, through Norway and Sweden, to the Arctic island of Svalbard. And this mountain belt was formed through the collision of the two ancient continents of Baltica and Laurentia after the closure of the Iapetus Ocean. And during this continental collision event, the leading edge of the continent of Baltica was subducted under the margin of Laurentia, in which the edge of the Baltican continent was metamorphosed to ultra high pressures, and then it was subsequently exhumed or brought back to the surface to its present day exposure in Norway. So yeah, the Western Gneiss region is situated in the lowermost basement unit of the Scandinavian caledonides, so right over here in Western Norway, and it's mainly composed of gneisses, of which most of them are amphibolite facies, so record later overprinting of lower pressure conditions. However, within the gneisses are found many pods of a darker mafic material known as eclogite, and it's in this that we still find the best record of the ultra high pressure conditions, and these were the rocks which I was looking at. And within the Western Gneiss region, the ultra high pressure conditions recorded can reach a maximum of 800 degrees C and greater than 28 kilobars in pressure. And these highest pressures are mostly found in the western region, in the western end of the Western Gneiss region, and there are even some localities which contain microdiamond, and then as you move east you kind of get lower peak pressures found. So rocks showing evidence of ultra high pressure metamorphism can be found in many localities around the world. However, the mechanisms of exhumation from the ultra high pressure depth in which they're formed towards the surface where they're seen today is less well understood, and a range of models have been for exhumation have been proposed that continue to be debated. One of these models, which is the model that's proposed for the Western Gneiss region, is called the adduction model, and typically this model is seen to have two stages of exhumation, whereby there's an initial phase of rapid buoyancy-driven exhumation, which brings the material from depth to towards the base of the crust with little cooling, followed by a second stage which has slower exhumation towards the crustal depth. So the Western Gneiss region is often considered the type example of this induction model of exhumation. However, validation of the model does require robust estimates of the pressure and temperature experienced across the full range of pressure temperature conditions which follow the peak metamorphism, known as the retrograde path. So the peak is up here and it follows this direction. And in particular, constraints in this critical key central zone of the path where the changes in exhumation methods occurs is quite often quite difficult to obtain, as the record within the rock is commonly gets overprinted by these late stages of exhumation. And I hope to be able to uncover some of the record of this central path, part of the pressure temperature path of the Western Gneiss Region. So moving on to my project specifically, it began in the summer of 2019 with 2 weeks of field work in my field area in Norway, which is a region called the Stadlandet Peninsula, where we were treated to stunning scenery such as this, but in compensation we did spend 2 weeks spending a lot of energy smashing big, really hard rocks with a hammer from morning till evening, because it doesn't really get dark in the summer in Norway. So my supervisor was quite hard to convince not to just work through the night. But anyway, it was good highlight of the project. So we collected over 80 samples of rock in the 2 weeks, which we then flew back with us to Oxford for the kind of real work to begin. So as said before, I was studying rocks called eclogites, which are primarily composed of the minerals garnet and anthracite. And anthracite is a type of pyroxene which is only stable at very high pressures. So as the eclogite gets exhumed to the surface, the anthracite becomes unstable and begins to break down. And as it breaks down, it forms exsolution structures called symplectites. And these are formed of lamellae of clinopyroxene and plagioclase, as well as some minor amphibole. And as the symplectites grow, they can preserve a chemical gradient, and this chemical gradient can be used to provide a record of the pressure and temperature conditions during these early stages of exhumation. And this is the kind of method that I aimed to utilize. So I began my project by looking at thin sections of selected samples, and I wanted to identify the samples which have symplectites which are still likely to contain this chemical gradient and therefore the PT record. So when this breakdown of anthracite goes kind of too far, the chemical gradients will be overprinted, and eventually you'll have large amount of breakdown to amphibole, which is kind of what's seen in this bottom thin section here. So I was particularly looking to select samples like these two top ones, where the symplectites only form in some cases a very thin rim around remaining anthracite, green mineral you can see here, and avoiding using samples where there are large masses of symplectite and even large amounts of matrix amphibole, as they're unlikely to record what I wanted to look at. So once I had selected my samples, I first examined them on the electron microscope, kind of taking photos and trying to identify symplectite colonies which would be suitable for my analysis. So these are actually the backscattered electron images of several symplectite colonies. So then I used the electron microprobe to take measurements of the chemistry of different points within a symplectite colony. So I took individual analysis plots on the microprobe, used at triple junction points of the 3 mineral phases present within the symplectite. So the black that you can see is plagioclase, the paler grey is clinopyroxene, and highlighted in purple here because they're quite faint to see them in these images is the amphibole. And I needed to take them at triple points because for the thermobarometry work you need all 3 of these phases in contact. So over a single colony I would take lots of these triplet points, trying to follow a transect following the symplectite growth direction, which is the fattest lamellae would have formed first and the thinnest are the last forming lamellae, and this is a temperature related growth. So once I'd taken these analysis, I calculated the pressures and temperatures of each triplet point using conventional thermobarometry methods, which are based on mineral exchange reactions. So for the temperatures, I used the Holland and Blundy whole-blown plagioclase thermometer, and for the pressures, I used a program called Thermocalc AVP. And so combine each of these red points here are the combined pressure and temperature outputs for each triplet point of some analysis, which I then, when you kind of put them on a graph for many points, so one of these graphs represents all of the analysis from several different symplectite colonies found in one sample. We have a pressure temperature plot from which we can try and constrain the pressure temperature path for this sample, and further constrained using up here are the peak pressure temperature path from the peak PT points from other studies, and from this we can try and constrain the shape of the exhumation path. So in total I calculated 6 of these pressure temperature paths across my field area, and we found that several of the paths had a fairly kind of, well, from the PT points we found that they did indeed have this clear 2-stage exhumation path with the steep initial decompression followed by a more gentle cooling at depths, with the inflection in the path around 10 to 15 kilobars at 650 700 degrees C. And so this path shape following the adduction model is typically interpreted to record this initial rapid buoyancy driven exhumation followed by a slower exhumation. And so we hope this confirmation of the 2-stage exhumation paths in the Western Gneiss region can help to constrain the models of exhumation and in turn provide insights into how the ultra high pressure terrains exhume more globally. And kind of in addition to this, my work that I did in this project follows on from a similar project done a few years previously by another Oxford master student, and collating my data with his, we both found that most of these kind of clearest 2-stage exhumation paths are found more towards the southeast region on the mainland of the Western Gneiss region, while the samples to the west on the Stadlandet Peninsula and in this other study further north in the islands tend to have a straighter path. And from this we potentially have a hypothesis that there may be some sort of tectonic discontinuity in the Western Gneiss region, kind of at the potentially running through the base of the Stadlandet Peninsula, meaning that maybe at some point in the subduction exhumation history this part of the Western Gneiss region was separate from the mainland, and if this turns out to be correct it would cause potentially some alteration of the current models of the Western Gneiss region exhumation. However, kind of in order to evaluate this hypothesis more clearly we would need kind of more evidence than the and constraints that the current samples we have. So what next? I'm currently hoping to write up this work into a paper. It would be nice at some point to develop this work further, whether by me or some other student. I think a good thing to have would be our own constraints on the peak pressures and temperatures, which would constrain these paths more. And of course, calculation of this method for a wider variety of samples would also be good. But currently I've moved on to working for my PhD, I've moved on to working for a different part of the Scandinavian caledonides. I'm now working on the Curly-Nap complex in northern Sweden, which is this green unit here. And this is an allochthonous unit formed from the outer margin of Baltica and contains lower grade metamorphic rocks formed earlier in the history of the Caledonian mountain belt. And I'll be conducting thermobarometry and dating studies, such as uranium lead dating of zircon, to investigate the metamorphic history of this unit and how this fits into the overall formation of the Caledonian mountain belt. So yeah, I'm looking forward to looking at a slightly different chapter of Caledonian history. So yeah, thanks everyone. So
Thanks, Izzy. Yeah, brilliant talk again. Thank you, and thank you to Sophie as well for a fantastic talk. So if anyone's got questions for Izzy, again, pop them in the chat. I know that there's been questions kind of being asked and being answered in the chat throughout that talk as well. And I guess I'll start off with a question that I have whilst we're waiting for people to put stuff in the chat, which is, it's just going back to your PT paths.
yeah.
Izzy, you'll know more than anyone that I haven't done metamorphism for a good few years, and it's not really my forte, so apologies if this is a really simple question. But what's the kind of dynamics that's driving the kind of sharp kink in the path? Why do you go from one dynamic regime of whatever this abduction kind of exhumation is to another? Is there a known answer for that, or is that
I'm not sure. I feel like with Richard here, I'm probably gonna say something wrong, but I'm not sure it's completely known, but potentially it's due to the kind of dynamics of it kind of, as it reaches the kind of base of the crust or the lithosphere, potentially that kind of slows the exhuming bodies down.